I'm gonna start recording. Cool. Let's jump into. Okay, so um, uh, you know how I like to start doing this. Um, what do we? What do you remember about binary search? Anyone? What is binary search?
It's logarithmic in time complexity.
Logarithmic time complexity.
Is that n log n, or is it just log n?
Log n.
Log n. Thank you.
Logarithmic time complexity. I don't know if logarithmic is spelled with 1G or 2Gs.
I think it's one. It's 1G for that. Yeah.
Cool. Thank you. Okay. Hopefully we'll get a sense as to why that is. What else?
Since it's binary, that means it's pi and we divide by 2. So we look for the middle index and we start looking either left or right.
That's correct. Divided by 2. Like this is the binary part. Or also like we can think of having 2 choices also.
Yes.
Choices. Cool.
Doesn't it work on, like, sorted data structures, right? Like it would only work because that way you'll know for sure if you're at like a middle and whether to search left or right.
That's exactly right. That's a very good point. Did everyone hear that?
It should be sorted.
Yep.
Sorted data structures. Yes, only works on sorted data structures.
And
what are? Oh, sorry. Go ahead, Siam.
Then we compare to find out like which side we're gonna go, either right or left.
Right. That's kind of like the 2 choices here.
Okay.
What data structures can be sorted?
An array. I've never seen this on like a set, but I'm assuming you should be able to do something similar to it. If not, because you can sort that. I'm not sure. I'm not sure about that though, because it can hold many different types of variables. So I don't know how that would work. So.
So a set cannot be sorted because a set under the hood is like a hash map.
Yeah.
And we know that the hash map cannot guarantee any order. Yeah. So sets can't guarantee any order, therefore they can be sorted. What else can be sorted? And this is like a linked list could be sorted, right? However, we cannot do binary search in a linked list. And that is because of the next condition, which is we need to, for binary search to work, the data structure needs to be I was going to say it needs to be indexed. And what this means is that we can go to any element in constant time. So the data structure has to be order, and we need to be able to go to any element in constant time by its index. So that removes linked list from our list here, but we can have a binary search tree. Binary search tree, which is a tree specifically with this property of having been able to search. I think that a binary search tree is not indexed. Like you cannot get to any element in constant time, but it is sorted. And if you go to the left or the right subtrees, you get access to the entire left subtree or right subtree, which then can help you, which then will allow you to get through the rest of the tree. So even though it's not indexed, so that's why I was doubting a little bit about this part here of index. Let me check. I think we had some other language here. Yeah, the collection must be able to access index in constant time, but that's the array. I guess something that I just realized that so can unify the array and the binary search tree is that getting to the next element, getting to the neighbor elements. Let's say in the array, you look at a number and then you +1, you can look at the next number. -1, you can look at the previous number. In the binary search tree, you can, to go to the left or to the right, you can just do key into the left or key into the right in constant time. Needs to be indexed. Yeah, this one is a bit, let's put like a star in this one, because index doesn't fully apply to binary search tree, but it's this concept of being able to access the element in constant time basically without having to loop again, or without having to do any other operation. Which in the binary search tree, we can just key into left or right. In the array, we could just add 1 or subtract 1 from index. Any other things about binary search that you might remember?
That the input needs to be dramatically large for it to get above, like, even just 10 splits. Like it's as the input grows, and this goes into the logarithmic time, but the length it takes to make the search doesn't necessarily increase. It's a very slow increase.
That's exactly right. And yes, that goes in the logarithmic time. Okay. Also, the basic, what is binary search? Like what's the defining word for binary search? Is it an algorithm or a data structure?
I think it's an algorithm.
Mm-hmm.
Yeah, because like you can also make like slight changes to it depending on what you're looking for. So it wouldn't be like a data structure. It's something that you can alter, I think. So
that's exactly right. So let me put that as the first thing. Is an algorithm. Algorithm. I forgot how to write algorithms. I know there's an M. Hold on. Like that, I think. Cool.
I think
An algorithm. And an algorithm is basically an algorithm is just, a series of steps. Series of repeatable steps. That's really what any algorithm is. Cool. Okay. Yeah, these are the main points. Let's check. So a classical example, and if you haven't watched this video, you should watch it. This is like the CS50, which is the computer science introductory course from Harvard, and their teacher is like amazing to explain a lot of the concepts. And computer science concepts. And he demonstrates an example there where one real world application of binary search is if you're looking for someone's name on a phone book, which nobody uses anymore, where you can basically search for a name of someone doing just looking at every page, seeing, let's say we're looking for John Smith. So we know that the phone book is sorted, is alphabetical, is ordered alphabetically by the first name. And we know that the person we're looking for starts with letter J. So we could just look at every single page, at every single name in the phone book until we find J, or we find the names that start with J, and then we can search for John Smith there. That will be a linear algorithm, because if you have a phone book that's 1,000 pages, then in the worst case, you will need to flip through the 1,000 pages to find John's. Or I guess like J is like actually I don't know where J is in the alphabet. Would it be around?
I think it's like 10.
Say that again, Marvin.
10. I discounted. I forgot as well. So it's like, hold on, do I even know that? Yeah, it's 10.
I think it's like around. It might be around the middle. Let's look it up.
7 letters or something.
Alphabet. The English alphabet. Here we go. J actually is in the lower half. But let's say Y it will be on the latter half, right? So the point is, let's say we're searching for someone on with a first name that starts with Y. Then let's say we have a phone book of 1,000 pages. That could be maybe in like page 850 or something like that. And if that phone book, is double in size, then we're gonna have to flip even more pages to get to that name, right? So that's a linear search algorithm. If we look at every single name on every single page. Binary search, which is most likely what you do when you're searching for a word on a dictionary or searching for someone's name in the phone book, is like you open it in the middle and then you check, you compare like J on what J or Y in this case, as I change the name of the person, on which half would it be? And then you know that is in the lower half. So that means you could just get rid of half of the phone book and then just focus on that second half. So if you had 1,000 pages, now you have a problem with 500 pages. And then you open that half in half, and then you look Y, where is Y? Y will be most likely to the right side or to the latter half. That cuts the problem into 250 pages from the 1,000 initial ones, and so on. And we can just keep repeating that step until we are only left with one page, in which case then we can find if the person with name Y is there. And if it is, then return true. If it's not, return false or return -1 or something like that. And that is then binary search, where we're splitting the problem in half at every time, which means that if we have, actually, let's do this. Let me open up this. So if we have 1,000, let's say we have 1,024 pages. So if we divide that in half, then we get 512. And if we divide this into 2, we get 264, I think. Is that right? No. This is embarrassing. I should know my math. 512 divided by 2, 256. Oh, yes. And especially this math, because this math is like 256. And then this divided by 2 is, don't remember.
128.
28.
128. Oh, how did that change? 128, which is gonna go 64 and 30, 32, 16, 8, 4, 2, and 1. So if we're searching for someone's name in 1,024 pages, we will be able to find that person in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 steps. Right? In 11 steps, we are able to find it, as compared to the linear algorithm where we have to loop 1,024 times. Here we just looped 11 times and we were able to find it. We're sure to find it or to know that it's not there. Because at each step, if we have an array of 1,024, we're dividing the problem in half. Cool. And what if we duplicate? What if we duplicate the size to double that, which will be 2,000 and
248.
say that again. 48.
Yeah.
So how many steps would this time take to either find the name or realize that it's not there?
12.
12 steps, right? And if we keep going, if we do, what will be the next one? 16, and 8, 9. Is this right?
I think it's 4.
I think so.
96, I think.
Yep. 2. Yes. Then if we have 3,096, it's going to take 13 steps. So you can see how we're duplicating the input size, yet it just takes one more step to complete. So if we have, and that this formula, or what we're expressing here, is in turn the logarithmic function. If we, because let's do this actually. Let's do log 2 of 1,024. So we get 10. And here, well, I guess like this one doesn't really count. The last one, the last one doesn't really count there.
It will just be
we have
thing, right?
Say that again.
We'll just be returning what we search for at that point, right?
Yes. Once we get to 1, like we'll just return what we're searching for at that point. So that logarithmic log 2 of 1,024 is 10, and if I do now a logarithmic of 3,098, 96, I think it was, we get 11.5. And we got here, what did we get here? We got 12 steps, but it's almost there. Let me close this. 248. What did we get? Get exactly 11. But yes, this goes to what Douglas was saying. Like the slope is really slow because we're duplicating the input. And if we map this out to a graph, then you get this graph, which is in the time complexity cheat sheet. Big old cheat sheet. That is logarithmic is here all the way down here, and it's so is this green one. It's just like it's so small because of it's putting contrast with the other ones, but it will look more. Let's say log 2 graph. Let's see what we get. Yeah, it will look more like this. It starts and then it goes in a very slow slope. And it never fully like pans out. It never gets completely vertical. It's going up, but it's like a very, very slow slope. And this is the logarithmic is sort of the opposite of quadratic, and that's why you get if you have both, you get the opposite graphs. So yeah, I wish I had a bit more of the math context to explain a bit further there, but they are the opposite of each other. And if we put them on a graph, they will look exactly as the opposite. So quadratic, or not quadratic, exponential, exponential and logarithmic. They are the opposites. Cool. Let's see, what is this one? Log 2, log 10, but yeah, they're basically the same there. Cool. Okay, so we get that. For binary search, the conditions are having the collection or data structure sorted and being able to access elements fast. So the algorithm is simple in terms of, it's simple for us to understand, like look at the middle and then decide. And then let's say the classic is you have an array of numbers and you're searching for a number, you're searching for a target in the array of numbers. And based on that, you look at the middle of the array. If the number is less than, if the target you're searching for is less than the number in the middle, then you should search the lower half. If the number in the middle is greater than, you should. If your target is greater than the number in the middle, you should search the right half. So the steps are: find the middle index, check the element at the middle index. If the element at the middle index is greater than the current target, than your target, you should go to the left. Otherwise, you go to the right. And then yes, decide whether you search the right side or the left side. Okay, so since this is an algorithm that we can just keep repeating on halves and halves of halves, we have two approaches. We have the iterative approach and we have the recursive approach. Both work fine. We'll see first the iterative approach here. Also, binary search is an algorithm that you can memorize. It's pretty simple once you understand it. Is there anyone here that will think that they already know it, that they already memorized binary search?
I think I got it, but I may be a bit like rusty on it. Doug, do you want to take this? It's
Yeah, no, I've got a pretty good handle, I think. on how it could be implemented. I was thinking on the recursive variety, but the iterative, I think I've got a better handle on how to do.
Got it. Okay. So that gave me the idea of let's take 5 minutes. Let's take 5 minutes to try to implement it using this array that I'm gonna give. Which I think is actually here. I'm gonna post it in the chat. So write an algorithm to search that array where your target is 3.
Again, excuse the billion things I have open. Oh, that's the wrong screen. There we go. All right. Let me see if I can add some zoom on this.
Mm-hmm.
There we go. Is that easier for folks to see?
Yep, this is good. Thank you.
Not a problem. Stretch this out a bit. So my approach was to assign a minimum and a maximum and a pointer, where the minimum would be just set to 0. The maximum would be the array's length that we're taking in as input, -1. And the pointer, this is where I couldn't remember this part. This is probably where I'm getting it wrong. But we want to try to take the minimum and the maximum and then divide that by 2, and then find the floor of that. I remembered that part of things. So then I set up a while loop. So while the pointer does not equal the target, I could have probably put in also a different search, but the first thing I asked is if it does equal the target. This I had originally had up as a new line, as a catch to find out if the pointer just happened to land on target before we even looped, to catch that. And I was like, oh, maybe I need to move that inside my for loop. So that's where I left off before we started. But there needs to probably be a better check at some point while I'm within this while loop to find out. But basically, after there needs to be some sort of check to find out if it's true. But if not, then we need to reassign our minimum or maximum and pointer depending on whether or not the pointer is less than or equal to the target. Also, just realize now too, we need to this needs to be like array at pointer rather than simply the pointer itself, or that's going to throw things off.
Nice. I guess does anyone have any comments or anything that they have differently or any thoughts on Douglas code?
I see one thing on line 6. Your pointer, you're establishing sort of like the middle there. I think that should be within your while loop, because you want to reset that middle every time you shorten your array. So that way that division keeps happening. So you don't want to establish it outside of your loop. Otherwise, you're going to be looking at the same place every single time.
Oh, that's good to know.
I would move that in. And I wrote my conditions slightly differently. I, instead of having a min max is relatively the same, I had mine's left to right, so that it's exactly the same in regards to that. But my condition was well, if we're using the min max, it'll be while min is less than or equal to max. It has a firm stopping point.
And yeah, let's change it to that, and let's think about what that means. So it will be as long as min is less than or equal to max. What does that mean? If we're thinking about the pointers, yeah.
Oh, sorry. Well, it would mean, well, the pointer. Okay, let's say if we start off and our target's not in the middle and we have to search the left side, right? and we shorten our array, and we have to find like a new middle. As long as the 2 pointers aren't like the same thing, it's going to run the loop again. It's going to continue running the loop, and if it doesn't hit that line 8 condition and return what you want it to return, it's going to keep going until both pointers are the same, which means that we've searched the entirety of the array, which means it'll break and then it will return false on the outside.
That's correct. That's correct. The two, like you can think of it like having 2 pointers at both ends of the array. And the while loop is as soon as those pointers meet, then that means we searched the entire thing and we couldn't find anything, as Marvin explained it. Great. Awesome. I guess like also since you moved line 7 in, we can remove line 11 and 14. Okay. Is there anything else anyone else looks at that might be interesting?
Just returning the index instead of Boolean values, I think.
Yeah.
That's fine. That's fine. We could leave it. We could leave it return
Okay.
true or false. There's one part in the math that is actually there's 2 things in the math.
Isn't it
Yeah.
supposed to be another parenthesis between max my? Well, you have to do, first of all, you have to add the max plus the min, and you also need a parenthesis between max and min. So before you divide it, yeah.
Great. And why do we need a parentheses?
PEMDAS, right?
It's yeah, I think it's that order of operations thing.
Yeah.
Exactly. Exactly. Because if not, then it will do this operation first. The division will be done first. Okay. And the max originally Douglas had max minus min. What is max minus min? Why is that?
Oh, I couldn't remember the way around, but it felt like adding like because with one starting at 0, I for some reason I thought it would be like the number would be climbing instead of, but I mean it's still doing the same thing if you're adding and then the min is shrinking or the min is growing.
I guess like let me see if I have any good thoughts here. Is that our pointers they want to meet at some point, right? If we're subtracting, we're just looking at the wrong. We won't calculate the middle in between these 2 pointers. We'll be calculating something outside of the pointers. And the adding, make sure that it's in between those 2. Cool. Okay, let's try it out. Let's see if it works, or if there's anything else sees. Got it. Cool. Okay, questions or thoughts? Does this make sense? Maybe not.
No, it does, but thank you so much for helping me like get the rest of the way to remembering how to implement this.
Awesome. Other questions or thoughts? Anyone? So with this array, it's a bit hard to see the efficiency because this is a small array. So I just made a larger array. Why don't we try it out with this one? Actually, also before we do that, Douglas, could you maybe console log? Could you console log maybe inside of the while loop? Maybe console log the element at the pointer or the pointer, any one of the 2. And I guess like, yeah, and before you run it again, how many times did this algorithm ran to find whether 12 was in the array or not? Anyone wants to guess a number? Or in other words, the same question is like, how many times are we going to see this console log?
I think it should be the 12 or the 7.
Let's say 12.
I put, yeah, if I put 12 in,
I think 3.
I think
Okay, so see how much it's going to be 3. Marvin says 3. Douglas and Johan, what do you say?
maybe once, as it would, the pointer would, it's going to start in the middle, and then the pointer's not going to be there, so it's going to try to move. Actually, no, you're right. Maybe it'd be maybe 3. Yeah, it's got to be 3.
Mm-hmm. Let's try it out.
Yeah, there we go.
Nice. We get that. So he looked first at the 5, which is the middle, and then he looked at the middle between the 5 and 9, which was 7, and then both pointers actually met at 9, and he checked 9, and that was not the one, so we exited. So let me share this here. Let's see if let's see if we can see it happening with a larger array. I just made an array that is 1024 elements. Let's see to confirm what we were talking about. All right, I guess like, so I'm just gonna paste it. I'm just gonna paste it in this chat. I don't know if Zoom. Oh, Zoom doesn't let me paste something really long.
put like a limit on it or something.
Yeah, hold on. I can share the file then. So I just sent the file so you can download it and then paste that array. And I'll do it here so we can see it. Let me share my screen again. Okay, and I'm gonna put my giant array in a separate file. So I'm just call it array.js, and I'm gonna paste it here. So this array has it has 1,000, exactly 1,024 elements, and let's search for this number here at the end, 99,353. So I'm gonna I'll make sure I export this to I always module that exports because this is not React array. I have my array. Now I'm gonna I have this binary search here. This is just the same. It's the same one that Douglas has. I guess there's one slight different, which I can fix it. Less than or equal to. I did, instead of less than or equal to, just less than, and then in high instead of -1. Yeah, I think I was playing with this +1. And this is returning the index, the indice, instead of true false, but it's the same thing. And I have here a console log for the guess. So let me import my array here. Let's call it array equal require file with the same name. I'm gonna feed that array here. We're gonna search for 9,500, which was 353, I think. Let's see. Yeah, 353. And let's see what we get. So according to our math earlier, if we're searching for, like, if we're searching 1,000, the logarithmic time of that was 10, right? So we should not see more than 10 console logs here. Let's take a look. Let me expand this. And this, oh, I think, sorry, I think this is in my, since I was doing this in some other folder. Here we are. I'm going to say node binary search.js. There we go. So if it found it at index, oh, someone is joining with a phone. Wait, let's see who that person is. Hello. I don't know who this person is. Hello, sir. Can you hear me? Hello? Can you hear me? Hello?
Yeah, Alcatel. Hello, Alcatel.
Hello, sir. Can you hear me? I don't know if he can. It seems like he can't hear us. Hello, Alcatel. Yeah, I don't know. I put them in the in the waiting room. Has anybody seen that person before?
What was that?
I don't know.
I think it was
licking his lips. That's what he was doing. He was there, like licking his lips. I didn't know. I tried not to laugh, but then my mic kept coming off, and I was like, oh, "It's too late." Like,
yeah, it's. I don't know. I unless somebody shared a link or by some weird reason he ended up with the same link. Yeah, that was funny. This is the first time I see someone random come into my Zoom room.
I've never been in a Zoom call that's happened before, so that's
that's pretty wild.
Yeah,
So going back to what we were talking about here, this algorithm is returning the index at which it found the element, and found it at index 1018. And if we count this, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, exactly 10 steps this one took. But yeah, if we're searching for the last one or the very first one, it's always going to take 10 steps. It might take less. It's guaranteed to take less than 10 steps. Well, I guess it's not guaranteed to take less than 10 steps. It's, in the worst case, it will take 10 steps. It took just 10 steps to find this number in an array of 1,000. And if we double that, it's just going to take one more step. Which is why binary search is a cool algorithm. Cool. Does that make sense? Questions or thoughts, anyone?
Yeah, that makes sense. I think what's cool about this is I don't think I've ever like visualized how it was getting to logarithmic time and how fast this actually works, you know? So I think like, I understood the concept behind it, but the fact that it only took like 10 repetitions to cut through all of that is like kind of crazy. So seeing that in the console logs, it's really cool. So, yeah.
Cool. Yeah.
Is the space complexity constant?
Yes, in this case, it is constant. That's a good question. We're not using, there's no variable, there's no array, there is no object, there's no set growing as the algorithm is going. Other questions or thoughts? Cool. Okay, so this is the iterative approach, and it's pretty straightforward there. I want us to do an exercise before we look at the recursive approach. I want you to write binary search, same, but now you're searching a different array. You're searching, and I just thought about like how we can create a larger array. So here, let me show you this really quickly. So this is how I created that array of 1,000 elements. There is a node module called Faker, which you can use to get random data, like, for testing. You can get emails, you can get phone numbers, you can get names, etc. And then you can get numbers. And so I just had a looping for 1,024 times, and just getting a random number. I wonder what happens if I get a random Boolean. Oh, and you can see that it gets them random, but I had to sort it so that we could do binary search on it. So I just try, let's say Boolean, and let's say if it still stores it. Oops, I think this is node index. Awesome, yeah, I still sorted. All the false are in one side and all the truths on the other side. So, well, I guess, oh, I'm thinking that this has is it always roughly in the middle? It looks like it's always roughly in the middle. Yeah, it looks like it's always roughly in the middle, which is a good sign for the random, which is like well distributed. But let's just take this array. Yeah, I'm gonna take this array. I'm going to this created this JSON. No. Node index booleans .json. So I get this here. I'm just gonna cut it a little bit so it's not exactly in the middle, because I think if it's exactly in the middle, actually it's not exactly in the middle, but I'm just gonna move it a bit. So to do that, I'm just gonna cut a chunk of truths out. Maybe a little bit more. Oh no, VS Code formatted the array. Okay, so then there's this very large array. Let me send it. Let me send this on Zoom chat. I think I could just drag it. No, not as simple as that. I think I need to open it here, and then I can drag it. So using that, now I want you to use binary search to find. So the idea is to find where the first true is, but you have to use binary search for that. And this example could be like, this is actually something that could be gotten from like Git. In Git, you could imagine your history, the number of commits, and then at some point, let's say this false and true represents whether a given commit has a bug or not. So let's say if it's false, then there is no bug there. And then, the first commit, there was no bug. And then many other commits, there's still no bug. And at some point, somebody added something that introduced the bug. And then after that, then the bug is present in all the other commits after that, because the bug hasn't been fixed. So it's like your job is to find the index this time of the first commit, of the commit that introduced the bug, or the first commit that is true. now, but using binary search. So it's the same algorithm. You're gonna have to adapt it because now you no longer have numbers. You have true and false. Let me ask this. Well, actually, this array is sorted because it's sorted not numerically, because this is an array of numbers. I sorted that all the false are on one side and all the truths are on the other side. Does that make sense? Okay, so right binary search, iterative still, to search the first true in this array. The same approach, look in the middle, check what is there, and decide whether you move forward, on which half you go after that.
I couldn't open the file. It takes me to Atom, and I do have a problem with Atom. It doesn't open at all.
I see. Try to download it. Like, where it says show in Finder.
Yes, I did, but I have a problem with Atom.
Yeah, but you can right click on the file. Once you open it in the Finder, you can right click on the file and then say open with VS Code.
Okay. Okay, thank you. Yes, I got it. Thank you.
Cool.
Are we looking for the first true or the first false?
The first true.
I can literally, I don't think I need this portion. I think I could just put on the offset here. Just to return current. I think I can also, if array, so if array at current is false, that means that we're going to be looking on the right side, right? We're trying to look for that first true, right? So array at current is equal to false. What we'll do is that we will make left, right, equal to, I believe, right? We'll bring in the left side so we can look into the right side. So left would be the new, we'll update that, and -1 or +1?
Yeah, it will be your increase in left to be the current +1.
Yeah, because we don't want to include the current like still in that sort of like division. So that makes sense. And then
And also remove the, you don't need to key, you're not keying into it. You don't need to key into the array, just current +1.
it could just be current +1, right? Right.
Yeah. Mm-hmm.
And then this would also be if for the top I can do though. For this portion I can key into it, I believe, right? Or would I have to?
Yeah. This portion you need to key into it.
Yeah.
The way you're doing.
It'll be true, and then it'll be right is going to equal to current -1. That way we have it like that. And if we don't find it, we would just be returning -1 like you said before.
That's right. Also, since like the line 12 is that's the remaining if statement, we could just skip it and say that's an else. You know what I mean?
Yeah, so that actually makes a lot of sense. So, actually no, it would just be, I would get rid of this, and I would just put this in an else, right?
That's exactly right. Yeah, that will be an else.
That and then that a bit better. Cool. And then I believe
Let's try it out.
Yeah, node review. Yeah, that's right. 530. I got 530. It was 9, right?
What did Douglas got?
Actually, I was having trouble with the file, so I just made my own
Gotcha.
input. It's not as long, obviously, but it did work though. So and it's practically this to the letter.
Gotcha. Cool. Joanne, you said something.
Yeah, I was having trouble with the file too, so I just
created your own.
Huh?
You created your own?
Well, I actually copied the entire file.
Oh, okay, that's fine.
Like a module export, but that wasn't working out. So I went to REPL.
Oh, right. I guess, yeah, if you're in REPL, I don't know if that works, module exports. But yeah, 530 is what I got as well.
I was just making sure it was 5. I think before, when you got it wrong, it was 529. So I was like, oh, I'm 1 off.
Yeah, no, I was 1 off. My code was 1 off. But after I fixed it, is 130. And if you key into index 530 and 529, you will see that the previous one is false, and 530 is true. Siham, how did it go with this?
I get something else.
And you have
because I didn't do like if the array current equal to true and the current -1 equal to false. Why?
But do you see why that is important though, looking at the previous one?
No, that's why like I want to ask about the line 8.
Okay, yeah. So line 8 is because we want to find the first one that is true, meaning we need to be able to tell whether that's the first one. We need to look at the previous one to make sure that the previous one is false, because we might be looking at a true that on the one before and the one after is true, right?
Okay. Yeah, I got it.
Got it. Cool.
Basically, if you find like true and true, so it's gonna keep going maybe to the right or to the left.
Yes, it's going to go on line 12.
Yeah. Yeah, to the right, and then it's gonna check until that we find one is true, one is false, and then this is the first true. Okay,
that's right. Cool. Okay, questions or thoughts on this one? And this array is like, I think it's a bit less. It's less than 1,000, but same. We're still logarithmic time, so this is still happening pretty fast. In like very short amount of steps going on. Cool. And also it's interesting because it's sorted in this weird way where when we think about sorted, we think about numbers being sorted in numerical order, but this is sorted in this other way. Cool. Okay, so now let's think about how would we do this recursively. So let me share my screen here again. I have my stuff here. So let's first look at the first one, just recursively. So the recursive algorithm, in this case, I think is a bit, you'll see how it's actually sort of the same. Is the same, it's just that written in a different way. So let's see. Yeah, let's just start writing it here. This was bug commit. I'm gonna comment this out. And we're gonna say binary search recursive. Takes in an array. And we want this to be recursive. So we reviewed recursion last week. What are the ingredients of recursion?
You need a base case.
Base case. What else? Joanne?
A means of progression.
Okay, means of progression towards the base case. Oops. So it's base case, and we need, what's the last step?
It has to call itself.
The recursive call or call itself. Okay. Now we said the base case are generally like cases for which we know the answer to, or are like small cases. What would be a smaller case for this example?
If the pointer equals the target, but I'm just trying to think of the right way to say that. If we found our target.
Okay, yes, so that's one of the base cases. Other base cases.
Like if the array length is 0.
If the array length is 0, so if array length, oh, and I forgot to put a target or a value here. If the array length is 0, we just want to return -1. So let's put this here. Okay, if found target, so that means that we need to calculate the middle point and just check if that's our solution. So let's calculate the middle here maybe. I'm gonna say const mid equal math.floor, same thing. I'm gonna call it, oh, well, we still need high and low. Let's say this is gonna be high, or left or right, max or mean. Those are good names. High plus low divided by 2. And I need to define those. Const high, let's do low equals 0. High is equal to array.length -1. Okay, the next base case is the case that Douglas mentioned. If we just happen to find it, we happen to be lucky. So if array at mid triple equals or target, let's return the index, so which will be array at mid. Cool. Okay, I think we have our base cases. Now we'll have the other cases, which will be if
The bigger and
if,
smaller.
that's correct. So actually, I like to define a guess variable. just so that I can, instead of doing this, I do that there, and guess. This is our guess. If guess is greater than the target, then that means we need to go on what side? Guess greater than the target, that means we need to go on the left side. Else, search the right side. So how would we do this though? Actually, we need to do it recursively, right? So there's two ways. One is we could split the array like physically. We could call array slice. We could also use the same, we could also pass different pointers in the same way we were doing it with the iterative approach as well. Let's physically split here or slice the array. So if the guess is greater than the target, that means we want to call itself. We actually want to return call itself with call itself, but now this time is going to call itself with the right side of the array, right? So we can just slice the array. Say array that slice it at the midpoint, and then pass the same target. Otherwise, call itself, but now instead of the right side, we want to slice from the beginning to the midpoint, and call binary search again, but now this with the right side. Actually, I think let's just let me do it here so that I'm gonna call it left side. I'm gonna say, well, let right side. This is gonna be the right side, and we're gonna have that there, and the left side is literally the left side. Cool. So we do the slices 0 to mid. Oh, that's why I was missing here. The left side is 0 to midpoint, and then the right side is midpoint and onward or forward, right? And then if the guess is greater than the target, that means we are searching. Wait, the right side or the left side? They always. Yeah, the if the guess is greater than the target, that means we shoot too much on the right side. I think I got confused here. Yeah, and I had the comments and I still messed up. Yeah, search the left side. Otherwise, search the right side. So the sort of here the means of progression are like this kind of here, slicing, and the recursive calls are these ones, right? And sometimes the recursive call and the means of progression, like sometimes these two are like on the same line as I had it before, but it could also be a separate one. This And then this else return that. If the length is 0, return -1. Let's try this out. I'm going to try it out with the simple array that we had here first, with this small array. I'm actually gonna, yeah, let's just leave it here, and I'm gonna say remove that. Binary search nums, searching for 3. Let's try it out. Node binary search. Nice. It found it at index 1. That's correct. This is the answer, and these other are the console logs inside of. Oh wait, hold on. Am I running? I'm still running the old one. Recursive. So we don't know if it works yet. Oh, there we go. It still works. Index 1. It found it there. Questions or thoughts here? Also, this still needs one small fix, but any questions or thoughts up until this point, which is the main point? Okay. One point is the one fix that this needs is that this right now is good to search on the left side, but if he ever has to search on the right side, it's not going to work. Let's try to search for like 17. 17 still returning 3 for some reason. Oh wait, hold on. 3 1 0 1 2 3. Yeah, that's not our target.
Yeah, because we need to add, because like when you cut in the middle, then the index starts from 0 again.
That's exactly
We
right.
need to add the mid, or in here is a guess plus the value that the new index numbers.
So the way in which we do that, that's a very good point, Siham. Thank you for pointing it out. Is we're gonna, when we're searching on the right side, we want to make sure that we return the mid plus whatever this recursive call return. Exactly because of what Siham said. Because we're slicing, then this right side for the subsequent recursive call will start at 0 again, or the lows there starts at 0. So we need to remember the previous mid and send that one down. I think if we have this now, we have index 8, 0, 1, 2, 3, 4, 5, 6, 7, 8. Now we got the right answer. So when we're searching on the right, we need to add that mid. This is because we're physically like slicing the arrays, and also just so that we see that, let's console log here. I'm gonna console log array here and then guess next to it. In the recursive call. Oh, but I wish. Oh, wait, hold on. What? Am I still? Oh, we still don't know if it works. You see the recursive calls. The recursive calls are calling the old one. Recursive. That was funny. Okay, let's see now. And okay, we still got the right answer. So the first time we call it, is the entire array, right? And the midpoint is the 11, element 11. Then after that, we moved on to the right side. We get rid of the lower half because we're searching for 17. So the next half is this half, 11 to the end. So 11 to 21. And then the half this time is 16, right? And then 16, and then we're doing the comparison. I was skipping the comparison. We're comparing 11 to 17, which is what we're searching for. we realize that the guess is less than the target. So that means we go onto the right side, which we take note of that midpoint, which was 0, 1, 2, 3, 4, 5, 5. We take note of that in that mid 5, and we search on the right side. When we search on the right side, that's this call here, that's this line. So we go to the middle. The middle is 16. Is that less than or greater than the target? Is still less than. So that means we keep going to the right. So that's 5 that we got there, plus this new middle, which was 0, 1, 2. So that's 7. And then we go into the right, which then is this side here. And now that's that last half. When we calculate here, the middle point is actually 17 this time around. And we just, the mids that we had accumulated so far were 7 plus 1 of that mid point. That gives us 8, and we have our answer. Does this make sense?
It does, and this is also worse for space complexity because it's filling the call stack with a handful of calls before it actually processes through all of them recursively.
That's exactly right, and this is worse than the iterative because it's filling up is using a space in the call stack. Let's think about, well, yeah, this is an interesting question. It's using, what is like the time complexity is still logarithmic. What about the space complexity? Anybody want to guess?
Linear.
Siham?
Said linear.
Okay, it's not linear.
I would say it's also logarithmic, as we're filling it up with at least as many loops as we would have looped, or if it was done iteratively.
That's right. We're filling it up with the numbers of halves that we get to do, and that's the number of cuts that we do. And that's still logarithmic. So yeah, log of n, where n is the length of the array. Oh wait, hold on.
For the space complexity?
Yeah.
Time complexity.
Space complexity. But I guess, actually, this might be a bit more nuanced than I thought. This might be a bit more nuanced than I thought because we are creating copies of the array here, copies of each half. And those are occupying extra space. So like, yeah, I think, and I'm not sure I will be able to derive it, but on the last call, when we call it with the, this is the last call, right? When we call it with this subarray, the other arrays still exist in memory. They're not out of the memory yet. And if we count the total number of elements, actually, then it's like, I think this must have a mathematical expression that expresses it. Well, that was redundant. A mathematical expression that expresses it. But because you have n, yeah, this is like, you have n. We have n elements in memory, which is the first array, plus n divided by 2, plus n divided by 4, until we get to, this goes advancing like that until we get to, I think, n divided by n. And this must add up to something that I don't remember exactly, but I know that I've seen this, because this array with n elements exists in memory, but a new array, a new array is created with half those elements, and then a new array is created with half those elements, and that's the n divided by 2, which is this array, and then n divided by 4, it would be this array. Something that I just like also came to mind. This is the point is this is a very inefficient algorithm in space complexity, recursively, because even though we're going either left or right, we're still doing the right, like the right and the left side, they're still created, and one of is used and the other one is just hold on to it, but we don't use it. So like when we go on the left side here, there was still we went on the right side here, sorry, the left side, it was still created and it's still being held into. So if I think about that all halves are always kept, then I think this leads to n times n, or n, yeah, or n squared. I think, because at each step we split the array in two, but we still hold on to the two halves. So that looks like, oh, now what Siham said is making a bit. It's now I'm doubting about Siham said linear space complexity. At each step, yeah, no, I think I'm not sure I'll be able to get out of this mental loop that I'm in right now, where I am inclined to say that I'm still inclined to say that is logarithmic, not logarithmic, of n square. Yeah, I'm just thinking about the number of, let me see what happens if we do this. Yeah, I want to console log, instead of console log an array, console log the length. So the length is being reduced, 11, then 6, then 4. Oh, I guess like, we could do just like in the other ones we do +1. We could just also say it here, made +1. So that it's like a bit more half, but it still works. This oh, actually, this is interesting. We get 7. Wait, was that my original answer wrong then? 0, 1, 2, 3, 4, 5, 6, 7, 8. No. So then we can't really get this +1 here. Or if we do it here, we'll need to add it somewhere else. No, let's just leave it here. The number, I'm thinking of the number of elements in the array that we have. I think I see CM sent something. Let's take a look at that. Oh, for some reason it's not opening up. Where did Chrome go? Let's take a look at this. Oh. Pasted it twice. Recursive algorithm. Implementation in Java. Let's try to space. Space complexity says log of n, and recursion has a space complexity of well, the iterative space complexity of 1. But I think it's because this recursive, yeah, this is because this recursive, this is the other approach for recursive binary search, where you pass in the array, you also pass in low and high. In this case, the space complexity is log of n. But because they didn't do it here the way that we're doing it, which is like actually splitting the array. They just pass in a new low and a new mid. Yeah, I think I'm just overcomplicating it. Let's just say I'm unable to say exactly what the time complexity for this specific one will be, given that we're creating copies of the array here at each instance. I'll be thinking about that, and if I find something, I'll make sure to let you guys know. It will be recursive. The other approach is let's do it here. This approach, let me copy this, paste it here. Copy this as well, paste it here. Now let's call this recursive 2. Let me change it here before I forget. The other approach is recursively, but without splitting. Base cases are similar, and then we pass in the array. We pass in low and high plus the target. So when we call the function, we have to do, we call it with 0, which is low, and then high, which is nums.length -1, and the target that we're searching for is 17. So we need to pass those at the start. We no longer need these ones here. That mid stay the same, guess stays the same. We can still have this base case. Oh no, actually this base case now will be the same one that we had in the while statement, which is if low is greater than or equal to high, if low is greater than high, return -1. That means the 2 pointers met and we finished searching. So actually we probably do that like as the first thing. And then we calculate a mid. We have a length. We get rid of the comments. We already know what those are, the base cases. If the guess is equal to the target, then return mid. Otherwise, if guess is greater than target, we are going to pass, instead of the left side, we just pass the exact same array, but now the low is going to be equal to, for the new low, we go to search the left side. So the low stays the same and the high comes down, right? Yep.
Yeah, no, that's right. Yeah.
Low stays the same, and then high will now be equal to mid -1. And target is the same. Array is the same, but now on the right side, the low is brought up to mid +1, and the high is the same, and the target stays. We'll get rid of these comments here. Let's try this one out. Have all the other ones commented out. Binary search. Oops, we got an error. It has already been declared. Oh, that's because I forgot to change it here. As we get our 8, let's search for 3. Oh, I don't even know how to get that. Yeah, we get 1. Cool. This one is logarithmic in time complexity, logarithmic in space complexity. There is no memory that's growing. Well, the only memory that's growing as the algorithm is progressing is the call stack, the memory being used by the call stack, which at each step gets a call. Questions or thoughts about this one? Does it make sense? Any questions? This is a bit, we have to think of a little bit about that sometimes. So this is binary search. We saw a few different ways of implementing it, but the idea is always the same. Look at the middle, and then decide from there, you look at the left side or the right side, and repeat with that half, and so on. So I think I might have one more exercise that maybe I would like you to do recursively. Let me see if I have it here.
Is a merge sort an unsorted binary search?
Say that again.
Is a merge sort an unsorted binary search? Where like you're doing the same thing, I think, if memory serves. You're splitting an array in half, but then you split it into you fracture it into basically as many pairs as you can make it, and then you swap them if if necessary, and then you just continually merge back up into a sorted array.
So merge sort is not an unsorted binary search because binary search only works in sorted elements. But you said a merge sort is an unsorted binary search. No, but I think what you're noticing is that pattern that is the same step. You're halving your array at each step. And if you recall, the time complexity of this is log of n, and the time complexity of merge sort is what?
I don't recall. I know it's good, but I can't remember.
Yeah, is n log n. So is n times log of n. So the log of n is the splitting, and the n is the merging back up.
Gotcha.
Yeah. So yeah, that's a good pattern recognition there of the splitting. Okay, let me see the exercise. Yeah, this just goes a bit more in detail about what we talked about. Oh, I think that was I didn't think about this exercise. This one is something we could do as well. But let me think. Yeah, we could do this recursively. So using binary search, this time recursively, return the number of negative numbers in this sorted array. So this is still the same approach, looking at the middle, but this is something that we might think about. Like, how do we know, like, the number of negative numbers? It's not like we're finding the first negative number. We know how to do that. In fact, you're going to need to do that for this. But once you find the negative number, how would you be able to tell the number of negative numbers from there? Like does anyone have a thought for that?
I think I do, but
Mhm.
I've been rather vocal tonight. I want to give other folks a chance.
Okay. Anyone else wants to give it a shot? Joanne, Sihan, Marvin? You find the first negative number there. Can you tell how many negative numbers there are
I
in
think,
total?
do we have to sort the array first?
Well, the array is sorted.
Oh, for yeah.
Sorted in descending order.
Okay. All right. Okay.
So you find the first negative number, and then you need to tell how many negative numbers in total there are. Sihan.
Is that the target? We're gonna say the target of 0, and then check if the negative number, and I don't know, maybe it's like a 0, and then count data.
So I think I see Marvin said like it's sorting in reverse order. So
Marvin, you can't iterate.
well, I think I guess it will still be binary search, like you will loop over the end, but we don't need to iterate.
Right. Because we
yeah,
have the index, so we can just like do it's the difference between the length of the array and the index where we find the number at.
Exactly. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, and we have 10 elements. Wait, hold on. we have 11 elements. We have 11 elements, so 11 minus 8, 3, and then that's the number of.
Should we look for the target 0 first?
I see. I think I see what you mean. So this one is similar. This is a bit of a mix. This is similar to the one that we were looking for the trues and false, because you're gonna look at any number and you want to make sure that that's the first negative number you see. And to be able to tell that that's the first negative number you see, you need to look at the previous number and make sure that that previous number is either 0 or a positive number. Yeah, but you cannot search specifically for 0 because the number 0 might not be there. You need to check that you found a negative number and that the previous number is 0 or a positive number.
Okay.
Okay. So let's do this one. I'm gonna put back the code for. Is it here? No. For the recursive ones. Also, I don't think I share this. That is so wrong on my side. This is the code. This is the lesson that we're covering over. And this has the same algorithm. But now I want you to adapt it or like write it if you haven't written the recursive one, to find how many elements, how many negative numbers are there in a sorted array. So let's take maybe 7 minutes for that. And I guess I should have sent you the array as well. This is not bad. Oops, stop sharing.
I just started.
Okay. And Marvin, I know. Oh, I think you said you can't talk at the moment. Okay. Douglas, do you want to share your screen?
Oh, sure. Give me just a second to get my Zoom back up. Is this it? No. Is it? There we go. All right. Can you see my code?
Yep.
Yeah.
Okay, cool. So yeah, so as I also put like this gotcha here just to see how many times the recursive function was running. So as you can see, it runs. There it goes. It runs 3 times until eventually it gives up and gives me the 0.
Mm-hmm. Oh, so I think the base case should be instead of less or equal to max, it should be greater than or equal to max in line 24. It should be less than if min is greater than max. Return 0. That means they overlapped, because
Right.
they might still happen. That's like that the two min and max are like on the two sides of it, or like one of them is over it, and we don't want to return 0 for that case yet. So, okay, let's try this out. Let's see if this changed anything. Oh,
I'm going to try to clear this out.
Okay, so we're still getting 0. Then check the mid, looks good. Check is the previous one and guess is the current one. Okay, while guess is less than 0 and check is greater than or equal to 0. Okay, return array length minus mid, that looks good. If guess is greater than minus 1, then search the right side. Otherwise, search the left side. This looks good. I'm thinking about. I think it's the -1 in 938.
Yeah.
Because yeah.
Or just returning.
Let's try that.
Oh, let me try clearing it.
Still getting that. Let's put the mid +1 there, and then instead of is greater than or greater than -1, put if guess is greater than 0.
Still the same.
Let's make sure that we're not calling input 3, binary search 2. You don't have any other binary search 2s, right?
No, I even graded out too, just so I wouldn't accidentally call it. Ray.
I'm not seeing it.
That's the third input. 0. Should that be just input.length?
No, -1 is the right approach there.
Yeah. Maybe let me try one more, because I didn't actually run it like this. Let's maybe if I get rid of that.
Oh, actually, sorry. No, yeah, the length
Oh, that's a
is.
Stack Overflow there. Whoops. Let's put that back.
I didn't realize that the length. Um, yeah, no, nums minus length minus 1 is the right one. Let me see what happens if I do that on mine. Okay, mine still works. I guess like I'm comparing it to mine.
Be a REPL issue?
Maybe try refreshing.
No, I probably should do a straight up one of these.
Mm-hmm.
I think it's doing it. Oh, there it goes. I've got way too much open at the moment.
You should look into an extension called the Great Suspender. That extension puts your saying failed to connect. So maybe it's something with REPL.
Yeah.
The Great Suspender puts all tabs to sleep, which makes save in memory.
Huh.
Still going to 0.